Hello, all. Good afternoon, good day. And this is Anirban, and I'm doing my blogs on computer vision best practices, good practices, whatever you may say. And this is the next in the series. So, look forward to your participation in this. So, starting from where I left off in the previous blog, talked about image augmentation and image resizing. We talked about the various ways of resizing an image and how to do the augmentation in a proper way on the original size of the image and then resize the image and all that, and used various techniques of image augmentation and image correction, right? Image denoising and correction. Today I'm going to talk about little bit about deep learning and how to apply deep learning and transfer learning to a problem at hand in the most scientific way based on my recent learnings. So whenever we talk of deep learning, we talk of transfer learning at the same time, right? So what transfer learning is, that if we look at this picture, which is taken from the State of the AI report 2019 by MMC Ventures, and you can see this report here in the actual site, state of AI 2019.com, chapter 1, what is AI. So basically we know that in deep learning the feature extraction is actually automatic. We can't specify which features the deep learning algorithm should give more importance to. Probably it's this side of the image, this particular edges, or if the image looks this way, then ignore that part of the image. We can't do, it's all automatic. And this is in contrast to machine learning, where the feature extraction is very, very important, and it is generally done in consultation with a domain specialist. So, if we are doing, for example, a house price prediction, we need to know what features of the house are important for that prediction. Is it the square foot area, or is it the location of the house? Now, it may be very simple for a house price prediction, but not so for a problem in a particular domain, let's say biomedical domain, where we might need to talk to domain experts and extract the features of relevance for that problem. And of course, after that comes feature selection methodologies like chi-square test and whatever. But the collaboration between domain specialist and the data scientist is very, very important. It's important in both machine learning and deep learning. But in deep learning, as long as we have a good set of images, we represent a problem which represents the problem, the deep learning algorithm is going to take care of its own. And the next important thing about deep learning is basically we know we have been applying this. It is something called transfer learning. So transfer learning means we use the trained convolutional base of a model, of a pre-trained model, let's say the VGG16, which is trained already on millions of images on the ImageNet database. We use the weights of that model, but what we do is the fully connected layer, which is there on top of the convolutional base, we take that off and slide in our own new fully connected layers and train only those fully connected layers for the task at hand. So this is what we know as transfer learning. There are different ways of transfer learning, which is discussed in the book by Francois Cholet, who is the originator of the Keras framework, in his book Deep Learning in Python, and one can read that up. This is just a basic idea of transfer learning. There are multiple ways in which transfer learning can be done, and I have explained it in one of my blogs on corrosion detection, where I used transfer learning to detect corrosion on images. I use the VGG16, and I use that the base, convolutional base, and only train the final fully connected layers for the problem at hand. And we could show that it detects corrosion from the dark brown hues in the image quite effectively. So this was written roughly about 3 years back, and happy to say I got a congrats from Francois Cholet himself on the Twitter when I shared the link with him. But even saying that, so this is the basic concept of transfer learning, which is given here, the conv base with weights equal to ImageNet. and include top equal to false. This is very, very important. And once we say include top equal to false, it means that we are not using the fully connected layers, but using our own fully connected layers by flattening the output, and then training those fully connected layers for the task that we want to do for our purpose. In this case, detecting corrosion from other similar brownish images. Right. So, having said that, this looks all good, but this lacks what I've seen over the years, that this is not the professional or scientific way of doing this. Why that is so? Because one of the basic things is, my assumption here is that the VGG16 will work the best in this situation. So I have gone straight away for VGG16. But when I was doing a project recently, and in my experience with senior data scientists in big organizations, what I have seen is, whenever we use the word that I think the VGG16 is the best suited for this, or I assume this network is the best suited for this purpose, what I've seen is they generally immediately they say that's not the language of a data scientist. A data scientist cannot say that one particular network will work the best. To establish that, we need to try at least multiple different pre-trained models and choose the best. So that is one thing I have learned in my interactions with leads in big organizations with whom we have worked, that never assume, never say I think, always test it out. So, coming to today's practice, if I were to write this blog today, I would definitely not restrict myself to VG16, but try at least the basic, pre-trained models which are available out there as pre-trained with the millions of images on the ImageNet database. It could be VG16, it could be VGG19, Inception V3, ResNet 50, ResNet 101, DenseNet 121, and so on and so forth, right? And as we discussed last day, each of these networks may have their own input image size specifications. For example, many of these networks have input image size specification of 224 by 224. The Inception V3 and Exception have an input image size specification of 299 by 299. So we have to do the image resizing, keeping the network in mind, which network we are using, which model we are using, right? So that is the first thing, that we should not restrict ourselves to one pre-trained network, right? In this context, I quickly wanted to also touch base upon some of the advantage of deep learning, some of the advantages of deep learning that I have come across. And the first advantage I talked about is that the deep learning does the feature extraction automatically, and this is very important to understand. I learned this from in one of the conferences, right, organized by a reputed institution, and from one of the professors. And this was one of the important concepts that he used to describe this deep learning. So deep learning, the feature extraction is, there is no human intervention there, right? That is one important thing. Second important thing that deep learning provides is, we can do incremental training of the deep learning system. Again, this also I learned in a conference organized by the ODSC, from an industry expert, and we have been using this in some of our projects. So incremental training means, a lot of the time we can't visualize this, because we work with, let's say, the images given to us from an open source repository. We try our deep learning modeling, will test the accuracy, and once we get a good amount of accuracy, we say our project is done, we submit it. We can't visualize how the images are going to flow in batches in a production system over the months when people start using it, right? And at that point of time, one thing that I have seen is very important, becomes very important, is how to revalidate the accuracy of the model, and how to use the data which is being processed, and the validated data, the corrected predictions, and use that to retrain the model and increase the accuracy of the model. That is something which I've seen is a business ask in most projects. Business is very keen about this, and business is very keen about getting the maximum accuracy out of all the available models. So that's why the first two things become very important. In fact, I remember in my last project, business was so particular about getting an accuracy of 97%, and they said we'll not be funding the project if the accuracy is less than this. So that's why these 2 points become very, very important. Training various neural network architectures and checking the performance of each of these and picking the best one. Incremental training, how I can use the data which is being processed, feed it back to the deep learning model. The model could be a model which I've been using for the last 3 months, let's say, and the model weights have been updated, and I use that model to update the weights further by using that incremental data. Now, this is not possible in machine learning. If I'm using a machine learning library, if I'm using the model for 6 months, I need to keep track of the data flowing through the system for the 6 months. And I need to, catalog that data, preserve that data, and use the entire data to update the weights of the model starting from scratch. There is no way to update the weights of the model incrementally. That is one of the clearest advantages of deep learning. And the other important point I have found is the ability to use distributed computing, which brings down the training time. Now, this is very important in critical time consuming or compute intensive tasks like segmentation projects, where we are training a model for image segmentation, instance segmentation, etc., where it can take many, many hours, right, over to train over a few hundred images. They are using distributed computing, with really helps using GPUs, right? Cluster of GPUs really helps to do that. And libraries like PyTorch or TensorFlow are designed to do that. Now, you can't do this using a normal machine learning library. Yes, it can be done in machine learning, but one has to use specialized libraries. That's why NVIDIA has come up with the Rapids AI library to use distributed computing with normal machine learning stuff. But if you use the normal learning libraries, they're not optimized to use the cluster of computing nodes. There are other systems like Spark or Databricks or H2O which provide that, of course, but not the normal day-to-day machine learning libraries. So these are some of the important distinctions which I thought we should all keep in mind about deep learning. But then, how do we implement a deep learning in the correct way? So some of the things that I've learned is, when we are using the transfer learning, obviously we use a pre-trained model. We load the weights of the model from the ImageNet trained model, and we say include top equal to false, which means we leave out the last fully connected layer, right? And then we say layer dot trainable equal to false for the pre-trained model layers, and we add the our fully connected layers on top of that. So we first flatten out the output, so we get the output in a linear manner, because that's what the fully connected layer expects. The convolutional layers output a volume, so we have to flatten it out, and then we use the fully connected layers. Now, the configuration of the fully connected layers can have an effect on the accuracy. That's what we have seen. Sometimes it could be that two fully connected layers works best. Sometimes it's one fully connected layer that works best. So we have to experiment on these things, right? And the other important aspect that I've seen is, commonly is, when doing a classification problem, I've seen that many a times we use metrics equal to accuracy, right? Now, this is not a correct practice, because, as we all know, accuracy doesn't have a lot of significance in classification problems, right? In classification problems, what is important is the recall, right, or the precision, or the overall health of the model using the AUC score, or it could be the Mathus correlation coefficient, right? So in some cases, I've seen businesses very specific about getting the minimum false negatives. So in this context, what comes to my mind, the best example we can think of is the COVID testing, right? So false positive is when we say a normal person, we test him and say he's a COVID positive. That is still okay. I mean, tolerable, because a person may undergo some extra medications or whatever. He'll be okay. But false negative, which means a person who is having COVID, we say from the test that he's negative. That's a false negative. And if we say we have a false negative result, that person's life is in peril, right? So false negatives are strict no in many situations. So, for example, the last project that we did, we had similar such situation. Another project on NLP based classification, also same thing. False negatives business was totally not going to accept. So it is important that we state our metrics correctly when we are doing a classification problem, image classification problem. It could be false negatives, it could be the AUC. Keras provides these facilities, and we can pick that up depending on our requirement and not just base it on accuracy, right? Suitable selection of batch size, learning rate, use of prefetch, shuffle, these are very important. And the use of early stopping and reduce error on plateau callbacks. These are also very important. So we know this is how we create our trained data set from the directory where we have our images of various classes, right? And we can use the Keras shuffle and cache and prefetch. These are some of the best practices which prefetches the data into memory from the disk while the training is on, right? So we can read up these things on the Keras documentation. But what's also important is how we are monitoring when we are doing the early stopping. So in this case, for example, we are saying monitor equal to val AUC. That means the AUC value of the AUC metric of the validation data is what I'm going to monitor. And when that is maximized, I am going to stop it, right? And my patience is 20. So this is very important, how we set up the monitor in the early stopping callback, right? And in the model checkpoint callback. And we define the mode accordingly. So if I say false negatives, obviously my monitor is false negatives, my mode will be min, right? One another thing which is used in many Kaggle notebooks is the reduce LR on plateau. That is, instead of keeping the learning rate constant, a reduce LR on plateau, right? With the patience and factor, we can vary this and check. Generally helps, right? So this callbacks list is also important. Here I'm using checkpoint, early stopping, and reduce LR on plateau. This is also, I've seen, is one of the best practice, some of the best practices that professionals use. Just wanted to share that. Another important thing I wanted to share here is shuffling of data sets. So generally, when we do, I have seen the MNS example, if somebody recalls, we'll not be having, what we do is we have 60,000 data, and we take the 50,000 data as training set and next 10,000 as a test set. We test our model accuracy on that, and we say we got a good accuracy and our results are fine. But believe me, this is not going to be so when we are using a data with different types of pattern in it. So for example, in our recent project, so if, for example, the train data is such that it has multiple different patterns, and it is already representative of the sample, the accuracy will be very high on the test data. If on the other hand, some of those patterns appear only in the test data and not in the train data, the accuracy is going to fall. So it is very important that we shuffle the set of images. Even though we mentioned shuffle in the TensorFlow dataset, I know we have used that shuffle condition over there. But in my view, even though we use this shuffle here, uh, it is very important that we create our shuffled data sets. And we have seen that when we do that, we can get different values of accuracy in the different folds or the different shuffles. So we can create, for example, 5 such shuffle checks, which means we shuffle the images at random and create the the shuffled data sets, right? So this is my train data, this is my test data. In each of these, I am actually using the 80 20 split, but each of these are shuffled. So we have five sets of train and test data. And then what we do is we do check the accuracy of these five sets, take the mean of the accuracy values over multiple shuffle sets. And then this mean is what we compare across the multiple pre-trained deep learning models or networks. So this is a technique which I have seen that has worked for us, particularly in difficult scenarios, as we said, right? Shuffling of the images and creating multiple sets. So this is something like a cross validation we do in normal machine learning, right? That is absolutely must in case of image classification, because we have seen the accuracy varies. Sometimes it can vary widely across the shuffle shades. So we'll get five accuracy values for the five shuffle shades. And then we take the mean of these to determine the final accuracy which my model is giving, right? It could be a ResNet 50 or ResNet 101, whatever it may be. So that is very important. Right? Along with that, the augmentation techniques. Now, when we say augmentation, there are a few different things that we have seen that it has helped us in some of our experiences. One is we all know that in deep learning we always have a data augmentation layer, which is the first layer of the neural network model. We augment the data on the fly and present it to the neural network, right? Because these deep learning systems are data hungry systems. That's a must, that we already know. But what I have seen in practice in real life when we're doing image classification, it really happens that the data comes in a nicely balanced way, right? That if I have two classes, 50-50 of each class in 100 samples, or if I have 10 classes, you know 1,000 samples of each in 10,000 samples, which is what the MNIST data set is. But generally, it doesn't happen like that. What we saw is some of the classes, it will be very, very highly imbalanced data. So, for example, when we are doing a two-class classification, recent project, we had a class imbalance of 1 is to 100. So, one of the classes was very rare. It could be a defect type, it could be anything. That occurs very rarely. So, you might have a class imbalance of 1 is to 100. So, in such situation, how do we take care of that is something we have to think. And we might want to use the image data generator with a basically image data generator with a save to directory. So we use the image data generator to generate additional samples of the deficient class and save it till my ratio becomes 1 is to 1 of both the classes, 100 is to 100 of both the classes, whatever value we set. So that is what something we might want to do. Yeah. So as we keep on generating, we check that the ratio is becoming the same, and the deficiency, the imbalance in the data is being resolved, and then we can stop this process. So that is one type of augmentation. The other type of augmentation is test time augmentation. Test time augmentation basically means mm, it can use we can include combination of techniques in augmentation. One of them is test time augmentation. What this basically means is we can use different types of augmentation techniques on the data that we have, on the image data that we have. It could be brightness enhance, contrast enhance, it could be Gaussian noise, it could be image histogram correction and all that, right? Whatever we can, gamma correction. Once we do that, we generate, let's say, 10 images from each image, right? We do 10 types of correction, we generate 10 images. Now, what test time augmentation says, I've given the reference in this research paper, is use augmentation in same way in train and test data. That means if I use, let's say, five different types of augmentation in the train data, I store those images as my train data, and then I apply the exact same techniques on the test data, even including the amount of noise. It will be exact same. Then we use the majority voting to determine actual prediction while doing inference. So when I'm doing inference on image, let's say image one, I augment it five times using the same exact techniques I did while training the model, right? I augment it five times. Let's say the first one could be brightness enhance, contrast enhance, gamma correction, Gaussian blur, or it could be image histogram correction. So the five techniques, exact same way as in the trained data. Now I do my predictions on these five augmented images and take the majority voting of the class to determine the class of the test image. So it's one step more involved than just doing passing the test images and getting the prediction. For each image, we have to do these augmentations in the exact same way and take the majority voting. Right. So that sometimes have been shown all to improve the above reference. Basically, gives a detail of this. So that could be a technique. The data preparation, how I augment my data and store the augmented data, in the folders. This is in addition to the on-the-fly data augmentation which we have in the as the first layer in the neural network. It could include augmentation of deficient class. Right. Once we do the data preparation, then once we come to the model training, now, as I was saying, in a professional manner, we say for model name in model list. So now instead of using one model, we use a list of models. It could be ResNet 50, ResNet 101, right? We iterate. And for each of these model, we say for I in range len of shuffled sets. So if you have five shuffled shades, we'll have I going from 1 to 5. For each of these shuffled shades, find, so we'll have model, right? And then we basically train the model. And then once we come out, we take, then we have an array of mean accuracy measures for the models that we have. Now we say for in the outer loop, so this is what I found is a scientific way of doing the things, right? There are more on top of it, like experiment tracking and all that, which I'm not going into today. But just wanted to say that, I gave the example of the blog that I had written some 3 years back, and it is a good blog. I got congrats from Francois Chole. I mean, what more can one get, right? The originator of the Keras framework over Twitter. But coming to today's standard, what we have to do is this kind of things where we iterate through multiple deep learning models, we shuffle the data multiple ways, we use test time augmentation, uh, augmentation of the deficient class, because real data is not going to be very idealistic that okay, it's all balanced and everything uniform size. No, so the image resizing has to be done in the proper way, augmentation, test time augmentation, and finally taking the mean of the accuracy measures over the multiple shuffled sheds, and then using that mean to compare which model is giving me the best performance, and using that model for our purpose. So I've given the two references that I used in today's blog. I hope it can give some ideas to people who are starting up on this area and have some idea. These are some of the lessons I've learned over the years, not to assume that, okay, I think in this situation, the Inception V3 is the best, let's use it. No, there's nothing like that. I haven't seen any deep learning expert till this point of time who can say, looking at a data, that this is the technique which is going to work the best, use it. They will always say, try out different methods and compare the results, right? So that is very important. How I do my retraining of the model incrementally, that is important. How I use the model monitors, the various callbacks, the model checkpoint, early stopping, reduce LR on plateau, right? These are very important, right? And particularly the monitor, what I'm monitoring. If I know that accuracy is not the best measure for my model, why should I monitor and maximize that? Lot of the tutorials I've seen in binary classification, they use accuracy as a metric, right? That doesn't make any sense. Shuffled sets, I've seen many tutorials, they will take train and test, done. But if you just reverse it, use the test as the first 10,000 and the train as the next 50,000, that results could be different. It will not be different with MNIST because it's a very uniform data. But in real life, you will find that when we shuffle that data and use the accuracy measures across shuffled sheets, the results, it will never be the same. The accuracy will vary between a good variation, good range. And one has to take the mean of that to see, to determine what is the final result of that particular deep learning model that we're using for this particular situation, and then take a decision. So this is how it should go, right? This is the overall data preparation, model training. This should all happen in a proper way, in sequence, right? So with that, I will complete the session today. I hope it gave some ideas. I was trying to give some pseudo code and some code snippets to show how this can be done. I have given some articles. Yes, I will include these reference articles in the last slide, also in the reference section. And right. So with this, I'll conclude today's session, and thank you for listening in and tuning in. Thank you. Thank you all.